You have seen this triangle before. Row 0 is a single one. Each new row starts and ends with 1. Every interior number is the sum of the two numbers above it. Simple rules. But if you follow those rules far enough, the triangle stops behaving like homework and starts behaving like a map to combinatorics, algebra, geometry, and chance. Most people guess Pascal's triangle is just a neat number pattern, a curiosity for math posters. The math says otherwise. Each entry counts how many ways to choose positions in a row. Each row is the coefficient list of a binomial power. Shade odd entries and a fractal appears. The triangle is a compressed library of counting formulas. Start with a 1 at the top. To build the next row, add neighbors. The two ones in row 1 come from nothing plus 1 and 1 plus nothing. Treat missing neighbors as 0. Row 2 is 1, 2, 1 because 1 plus 1 makes 2 in the center. Keep going. The mechanical rule is addition. The content is counting. Read row n as n choose 0, n choose 1, up to n choose n. Row 4 is 1, 4, 6, 4, 1 because there is one way to choose 0 items from 4 ways to choose 1, 6 ways to choose 2, and so on. The triangle is a triangle of combinations. Every entry answers how many subsets of this size. Expand a plus b to the 4th power. The coefficients are 1, 4, 6, 4, 1, the same row. That is not coincidence. Each term picks a's and b's from 4 factors. The triangle encodes the algebra of distributing multiplication. Row n lists the coefficients of a plus b to the n. Slide a hockey stick shape down the triangle. Start at row 2, entry 2, that is 3. Add the entry below left, then below left again. 3 plus 3 plus 4 equals 10, the entry at the bent end of the stick. The identity says a string of diagonal entries sums to the entry one step down and over. The proof is a combinatorial story about splitting subsets. Color every odd entry one shade and every even entry another. Or equivalently, mark entries that are 1 modulo 2. The shape that emerges is a Sierpinski triangle, a fractal built from nested hollow triangles. You did not draw geometry. You only checked parity of binomial coefficients. Algebra filtered through odd and even becomes self-similar art. Flip a fair coin 4 times. How many outcomes have exactly 2 heads? There are 6, matching the center entry of row 4. Each row lists binomial probabilities for n coin flips. The triangle is a probability cheat sheet. Add the entries in a row and you get 2 to the n total outcomes. Counting and chance share one diagram. Here is the surprise. Pascal did not invent every pattern inside this triangle. Mathematicians across centuries recognized pieces of it. Indian and Chinese texts described triangular arrays centuries earlier. Fibonacci numbers appear along shallow diagonals. Row sums double each step. Powers of 11 hide in small rows. One addition rule. Dozens of disguises. Walk a shallow diagonal and you read Fibonacci 1, 1, 2, 3, 5. Read row 5 as a power of 11 and you get 11,155, 1155. In modular arithmetic, patterns restart at different primes. You do not need to master every identity today. The point is the triangle keeps answering questions you have not asked yet. Recap. Pascal's triangle builds each entry from the 2 above. Row n lists and choose k combinations and binomial coefficients. The hockey stick identity sums diagonals. Mod 2 shading reveals Sierpinski. Row's model coin flip counts. One simple rule generates a library of counting algebra, and probability, all in chalk dust. 5 puzzles, 5 diagrams, from paradox to pattern. You saw why Monty Hall rewards switching, why negatives obey strict rules, why the golden ratio hides in growth, why squaring the circle is impossible, and why Pascal's triangle is a counting machine in disguise. Season 2 is complete. Subscribe so you catch what comes next. Numbers have stories. This is Math Sketch.